Welcome to the next video in the Real Analysis video series, and in this video we are completing the exercises that we partially completed in the previous video. We're moving on to this exercise showing that if C is a real number non-negative, then it just moves in or out of a soup freely. But if it is negative, then when it passes in or out of a soup, then it flips it to an inf. So let's start on that proof. So first we'll consider this case, and we will show that, because what we're trying to show is C soup x is equal to soup Cx. And so we're trying to write, in particular, that one is a soup of some set, and so we need to show that this thing has the properties of the soup. To that end, we'll show that this thing is an upper bound on C big X and that it is the least of all of the upper bounds of C big X. So here I am proving that C soup X is an upper bound, and then here I'm proving that it is the least of all of the upper bounds. And then this is where I start talking about the case where C is strictly negative. But okay, so to show that it is an upper bound, we pick an arbitrary element, call it C little x out of C big X, and that means that little x is an element of big X. Okay. By definition of soup big X, we know that this inequality holds because soup big X is an upper bound. We multiply by C throughout, and we're done. Right? That's really it. Okay. Right, because this basically shows that C little x was some arbitrary element out of the set, and C soup x is greater than or equal to it. So it's just that easy. Okay. Next, let's show that it's the least of all of the upper bounds. So let's take any other upper bound, call it beta. And this is an upper bound on C big X, so what that must mean is that if you pick any C little x out of C big X, then because beta is an upper bound, it is bigger. Okay, we would like to relate this somehow to soup X, so let's go ahead and divide by C so that in a sense we're kind of solving for X. Now, because we have X, we can say that we can say something about bounds, right? So basically what this shows is that beta over C is an upper bound of big X, right? It is one of the upper bounds of big X because for every choice of little x, we get this inequality. Okay, well then, since beta over C is an upper bound of X, then we use the property. Oh, by the way, and at this moment we should be aware, though, that dividing by C is dangerous if C is equal to 0. So we probably actually need to separate out a special case where C is equal to 0. But in the case where C is equal to 0, right, if you imagine replacing this with 0 and replacing this with 0, you'll see that this, proving this equality is borderline trivial, and therefore I leave it as an exercise. So that's very easy. But yeah, so we should separate out this special case where C is equal to 0. In every other case, we are free to divide by C. And then we know that beta over C is an upper bound. Now, because in that case where beta over C is an upper bound, then therefore it has to be greater than or equal to the least upper bound. And then we get, by moving the C back to the other side, exactly the thing that we were trying to show in the first place. And so that concludes the proof for the case where C is non-negative. Okay. Now for the case where C is negative, I just try to relate it back to the case of positive numbers, right? I could subtract C to the other side, and now I have that negative C is a positive number. And then I can say, well, I know that positive numbers can just freely move in or out of a soup. And then once it's in, right, once the negative C is on the inside, I can separate out the -1 and move that to the outside, flipping to an inf in the process. And so then you basically get this equation, multiply by -1 on both sides, and we're done. Halmos. I think that actually might be a long-ish video. I don't time these things, but then maybe this is a good time to stop the video, and we'll pick up the last part of this exercise in the next video.